Today we're going to be finding rational roots of polynomial functions. Yesterday we used Descartes' rule of signs to figure out the possible number of positive or negative roots. We talked about the fundamental theorem of algebra, which tells us how many roots we should be expecting. And we also talked about if there is a factor of x, how many times 0 could be a root of the polynomial. Now we're going to zero in on, pun intended, how to find the rational roots. So a reminder what a rational number is. It's a number that you can write as a fraction using integers. For the most part, every root we've found so far this year has been a whole number, or if it wasn't a whole number, it was a fraction we found from a linear factor. So if we look at this quadratic right here, it's pretty easy to factor, but let's just take for a minute and say that we don't really have a good grasp of factoring. Maybe we're an Algebra 1 student, and we wanted to know what combinations of factors could possibly multiply out to get this. So the method that you would do is we need two numbers that multiply to get negative 18 and add to get 17. And there are lots of combinations of numbers that multiply to get negative 18. For example, if you look at this table here, here's a bunch of combinations of factors that multiply to get the proper first term and last term of that polynomial, but maybe the middle term isn't right. And from each of these factors, we get these roots. If we didn't know how to factor, this would be a horrifying experience. There's just so many combinations. So it turns out there's a way that we can list all of these possible roots pretty easily. So I'm going to come at you sideways here and not tell you the theorem yet. Let's list all the factors of the constant term. Remember, the constant term is the term that doesn't have any variables. So we got negative 6. We could multiply negative 1 times positive 6. We could multiply positive 1 times negative 6, so there's 4 different factors. We could multiply plus or minus 2 times plus or minus 3. So there's 8 different factors there. There's 4, and then the negatives of those, that's going to make 8. This next question is list all the factors of the leading coefficient. Leading coefficient is the number that you're multiplying times the variable with the biggest exponent. So our leading coefficient is going to be 3 for this. 3 only has 4 factors, plus or minus 1 and plus or minus 3. Now this next thing is prompting us, well, what if we take and we write a fraction in which we take each factor of the constant term, that's all these fellas, and write it over top of each factor of the leading coefficient. And what you'll find is, through very little effort, we have every combination of numbers that we just had over here. For example, let's say we took positive 1 over positive 1. That appears here. How about negative 1 over 1? That appears over here. How about positive 1/3? Yep, negative 1/3. Got it? Every combination that could happen over here, we get super fast doing this. That leads us to the rational root theorem. It's a list of all the rational numbers that are possible, I want to stress the word possible, that are possible roots of a polynomial function. They can be formed by placing each integer factor of the constant term over each integer factor of the leading coefficient. So we're going to do that problem again, but now we're going to do it not coming at you sideways. Apply the rational root theorem to list all the possible roots of f of x. Here's how we're going to label this. We're going to call this the possible rational roots, and in the future we're going to abbreviate that. So we're going to list all the factors of our constant. It's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, divided by all of the factors of the leading coefficient. And in the future, we're just going to call this possible rational roots. Less writing. Then it asks, which of these values from the list do not appear to be roots? Now, for this to be asking this question, it's implying we have to have more information. So we actually have this graph here. Let me bring this graph down here so we can see it. So essentially what we're going to be doing here, we're going to list the highly possible rational roots. Now, this is only possible if someone gives you the graph. If someone doesn't give you the graph, then we're going to have to try a different approach to this. But if you look at this graph, it sure looks like -6 is going to be a root. Now, it's possible if we zoomed in, it's not actually -6, it's just a number close to it. Well, does -6 appear in our list? Well, it does, because we have a +6 over a +1. I'm sorry, a -6 over a +1. So it sure looks like -6 has a strong chance of being one of these roots. What about this other one here? This other one here is between 0 and 1. The only fractions that I have between 0 and 1 are 1/3 and 2/3. And it looks to me like this is less than half. So I'm going to make the conjecture that the other highly possible rational root is 1/3. Now, both of those could be right. One of those could be right. They could both be wrong. How are we going to check? So we could plug these numbers into the original function. And that wouldn't be that difficult to do with this quadratic. But we're not going to be dealing with quadratics all the time. We're going to be dealing with polynomials of many degree, and that is going to be cumbersome to do without a calculator. So we're going to try synthetic division. We're going to synthetically divide each of these into this function. And if you remember, if we get 0 as a remainder, that means it is in fact a root. And if we don't get 0 as a remainder, it's not a root. I'm going to do -6 first because the calculation just seems easier. We bring the 3 down, then we're going to multiply the -6 times the 3 and get -18. And then we add down and we get -1. And then we multiply and we get 6. Now I was so confident here that this should have worked, that if I didn't get 0, I would double check my arithmetic to make sure that I did it correct, because this sure looks like a -6, and I'm not ever going to try to trick you on this. So that works. Our highly possible root, rational root, turns out it was a rational root. Now we could do synthetic division again for 1/3, but if we're left with a linear factor, it might just be simpler to set it equal to 0 and solve it. And we end up with 1/3, which is what we expected to happen all along. So, long story longer, what are the zeros of this fella? -6 and 1/3. And further, if we wanted to write this in factored form, using this method, obviously this is easy to factor without this. But if we wanted to write this in factored form, this would be f of x. And then for each of your solutions, you're going to subtract that from x. So I'm going to have x minus a -6, which is x plus 6, and x minus 1/3. Now, if you look at this, you might be thinking, that does not appear like it's going to give us what we need for our leading term, because x times x is x squared. We're missing this 3 here. If we put a 3 in front, our leading term is going to be 3x squared. We could also confirm our y-intercept is going to be the same, because 3 times 6 times -1/3 is -6. So this all checks out here. Let's do 2 more examples from the beginning. In each case, we're going to be given a graph, and we're trying to figure out what the roots are for this function. So step 1, we're going to list the possible rational roots. To remind you how we get this, I'm going to write out some words here that are not required for homework or tests, but we're going to put this in our notes. We want the factors of the constant in the numerator. In this case, our constant is 10. And then we're going to be dividing it by the factors of the leading coefficient. In this example, the leading coefficient is 6. So the possible rational roots is every combination of numbers from plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10, divided by every combination of numbers of plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That's a lot of combinations. There's 8 choices on top, 8 on the bottom. That's 64. Now there's some repeats in there. So it's not going to be 64 unique choices, but that's a lot of options. Then we're going to make a list of the highly possible rational roots. I can't stress enough, this only works if I give you a graph. If I don't give you a graph, well, you're going to have to try a different strategy for this. So let's see if we can figure out the ones that we think might be obvious. This sure looks like it's going to be 2. So I'm going to throw that one down. Between 0 and 1, this looks like it's less than a half. So what are my choices for less than a half? So I've got a half here. That's not less than a half. I've got a third, and I've got a sixth. 2/6 is the same as a third. So the only choices I have are a third or a sixth. This looks to me like it's more likely a third than it is a sixth. Now I want to also emphasize that this could end up being neither a third or a sixth, because even though this is the rational root theorem, we should emphasize this gives us rational roots. So there could be irrational roots. There could be a non-repeating, a non-ending decimal here. Could be a root that you couldn't write as a fraction using integers. But if it is rational, it's got to be a third or a sixth. And then over here, this looks like it's about halfway between -2 and -3. And do we have a combination for that? We do. -5/2. Now, once again, these all could work. Some of these could work and some of these could not. We are taking super educated guesses to eliminate many choices down to possibly 3. If this ends up not being a third, then I would probably check a sixth to make sure that that didn't work or did work. So the next step would be step 3. We're going to do synthetic division. Remember that we want to make sure that our terms are written in descending order with respect to the exponents. Our coefficients are 6. Well, the other thing we want to remember, make sure we're not missing any terms. This is cubed, squared, first, and then to the 0. We're not missing any terms. If we're missing a term, we want to put a 0 in as a coefficient. I would recommend that when you choose which of these to do first, either do the one that's the easiest to calculate or the one they're most confident in. 2 seems like it's going to be the easiest to calculate. Bring the 6 down. 2 times 6 is 12. I'm sorry, I wrote a 0 here with all that hot 0 talk. That's supposed to be a 1. My apologies. Let's double check now. 6, 1, -31, 10. I add and I get 13. 2 times 13 is 26. Add, I get -5. Multiply, I get -10. The remainder is 0. That tells me if the remainder is 0, then 2 for certain is a root, and that means x minus 2 is for certain a factor. Now I'm going to check a third or -5/2. A third seems easier because I'm multiplying by 1 and dividing by 3, as opposed to multiplying by -5 and dividing by 2. So I'm going to take this depressed polynomial, and I'm going to divide it by a third synthetically. And hopefully this works out. Bring the 6 down. A third of 6 is 2. Add, a third of 15 is 5. That remainder is also 0. Now, if I'm only left with one factor, I'm not going to do synthetic division. You can if you want. I'm going to change this into a linear function, set it equal to 0, and solve it. You might be alarmed that you get negative 15 over 6. It's not one of our choices up here. But you can reduce this. This reduces to negative 5 over 2. So that also is one of our roots. See, I got a little bit big here in my writing. So we're going to answer the question, and then we're going to one-up what the question asks. Answering the question, what are the roots? I like to write them in ascending order. If you choose not to do that, it's no big deal. And then the bonus thing that I want you to write down for your homework. On a test, answer whatever the question the test asks. But on your homework, I want you to write down the factored version of g of x. It's going to help us in later lessons to get this practiced. So we're going to take x minus each of our roots. We've got x minus a negative 5 over 2, so that's x plus 5 over 2, x minus a third, and x minus 2. Then we have to see, is this actually correct? Because our leading term is supposed to have a 6 as a coefficient. We're going to have x times x times x. If we put a 6 in front, that's going to make it 6x cubed. And if we were to multiply 6 times 5 over 2 times 1/3 times negative 2, we should get 10, and we will now that we've done that. Let's do one more of these, and I'll turn you loose. We're going to make a list of the possible rational roots. So we're going to take factors of 3 on the top. It's only a couple. Factors of 18 on the bottom. There is more than a couple of these. We're going to have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. If you have a lot, I would double check to make sure that you got pairs. So either I'm missing 2 or I'm not missing any. I'm not missing any. Then we look at the graph to find the highly possible rational roots. If you're not given a graph, we're going to have to do this differently, and we'll learn about that later. So it looks like to me, we're going to have a root between 0 and 1, and it looks less than halfway again. So my choices are a half, I think it's less than a half, a third, probably going to be a third, could be a sixth or a ninth or an 18th. I think it's going to be a third. Now, as we learned previously, if the graph is tangent to the x-axis, then that root has a even multiplicity. So this 1/3, if it appears once, it's going to appear twice. Now, having said that, if I zoomed in, it is possible that I come down here and I go through a third and it comes back up below the graph like this. Now, I wouldn't intentionally do that to you, but there are times when you use your calculator that happens and it's hard to see unless you zoom in. So if I get a third to work, I'm not going to assume it works twice. I'm going to check it to make sure this is in fact tangent to the x-axis. This one here appears to be halfway between -1 and -2. So that would be -3 over 2. Then we use synthetic division to make sure we're not missing any terms. We're not. Make sure they're in descending order. They are. We're going to divide synthetically. I'm going to do a third because that's easiest. 18, bring her down. A third of 18 means 18 divided by 3. And then I add, and then I multiply, and then I add, and then I multiply. I get a remainder of 0. 1/3 works once. Let's check it again to make sure it is in fact tangent to the x-axis there. Bring the 18 down, multiply, add, multiply and add. It works twice. So no one was getting tricked there. A third works twice. I'm going to take, once I have a linear depressed polynomial left, I'm going to set it equal to 0 and solve it. This is going to give us -3 over 2, which is the last one that we expected. So to answer the question, what are the roots? -3/2, a third, and a third. Yes, I wrote a third twice, and I would ask that you do the same. That puts some emphasis on a couple things. One of those being when we write this in factored form, once again, the directions in the homework won't ask you to do that, but please do it. We're going to have x minus a -3/2, which is x plus 3/2, x minus a third, and we'll write that succinctly by saying it's squared. And then if we multiply x times x squared, that's x cubed. We need a leading coefficient to be 18, so we put an 18 out in front. All right, that concludes these notes. We're going to continue to get deeper into the two things we haven't done yet for roots. We haven't found irrational roots yet, which is going to be coming up. We also have not found imaginary roots, which is going to come up here shortly. And for that matter, as far as rational roots go, we haven't done this when we haven't had a graph to pick highly possible rational roots. And that's going to be a little bit more involved. Thank you for your attention and have a good day.